Kinsyn 7 is a unique new computer program being developed by Kintech Incorporated. It offers unparalleled ease of use in the design of pin or slider-jointed linkage mechanisms of any topology. No prior computer experience is necessary because Kinsyn 7 uses a natural graphical dialogue. A cursor is positioned on the display screen simply by moving a pen on the surface of a data tablet. Objects beneath the cursor on the screen are highlighted. Clicking the pen button when a title on the screen is highlighted causes a pull-down menu to appear, listing options for the type of synthesis or analysis to be performed or the type of visual feedback which the designer desires. These options will then immediately take effect. On the left of the screen are icons representing pin or slider joints of various types. Clicking the pen button on one of these icons grabs the icon and causes it to track the motion of the pen. In the following example, a rotor tilt mechanism is being synthesized for a short takeoff aircraft. As the rotor tilts, it must shift in a carefully controlled way so as to keep the lift and gravity forces in balance. At this point, the designer has already specified two design positions for the rotor and is now in the process of studying various possibilities for where a moving pivot for a 4-bar linkage might be located. This first moving pivot will be used to guide one point of the rotor exactly through the two design positions. Picked up. The designer has now grabbed a fixed pivot. The computer is showing the link connecting the fixed and moving pivots. As the designer positions the fixed pivot, he's constrained to position it on the red locus, showing the points compatible with the first choice that he made. The designer is now positioning a second moving pivot. As he moves the moving pivot around at various points on the rotor body, the locus of possible fixed pivots is shown in this case as well. As the designer goes to choose the fixed pivot corresponding to the second moving pivot, the complete 4-bar linkage is shown. Arcs show the limits of crank rotation or the limits of rocker swing. The Grashof type for the mechanism is flashed at the bottom of the screen, as is the transmission angle for the mechanism being instantaneously examined. All of this takes place in real time. As the designer positions the joints for the mechanism on the screen, the complete coupler curve for the mechanism which is being instantaneously displayed is shown with red and green branches indicating the two modes of assembly for the mechanism, or the various lockup positions for the mechanism. Touching the word analysis causes the computer to go and perform an instantaneous and immediate analysis of this device. To immediately branch into the animation routines and see a complete position or velocity analysis of the mechanism. Here the linkage which was finally selected is being shown as it moves exactly through the two design positions. Picture files for use with Kinsyn 7 can be brought in from other computer-aided design packages, or else they can be drawn using Kinsyn 7's self-contained drafting capabilities. Branching between the synthesis and the analysis procedures is instantaneous. Simply touching the word "done" with the cursor causes an immediate return to the synthesis part of the program. Now the designer has gone to the plane symbol in the upper left of the screen and grabbed another moving object. touching the plane icon causes the picture associated with the moving coupler plane to jump to the end of the pen. That picture then tracks the pen motions. Now the designer has 3 design positions and is positioning a moving pivot for a 3-position synthesis. As the designer moves the moving pivot out onto the display area, the 2nd and 3rd positions of the moving pivot are also shown, and the computer displays the link which it is instantaneously synthesizing, capable of guiding the moving pivot from its selected number 1 design position through the other 2 required positions. Here the designer has picked a 2nd moving pivot. As the designer scans through the possibilities for the 2nd moving pivot, the computer shows the entire linkage in all its design positions. It indicates the Grashof type for the linkage, and if desired, it also displays such things as the transmission angles or the coupler curve for the mechanism. Now the designer has synthesized a 3-position mechanism and has selected the analysis options and is studying the behavior of this latest synthesized mechanism. The entire synthesis process and analysis process is taking place in real time, just as you see it on the screen. There are many display options available. For example, during the analysis, one can suppress certain parts of the mechanism, or one can display the mechanism in a storage mode so as to show the envelope of the motions. One can display the velocity relationships, or the transmission angles, or the coupler curve, or the pressure angles for slider mechanisms. These options are all simply turned on or off by means of the pull-down menus. As you see, this is an exact solution. Now the designer has returned to the synthesis part of the program and is specifying a 4th design position. Pulling the rotor assembly out and positioning it in its 4th position using the pen on the data tablet, the designer now is rotating the rotor into its 4th position. And the Burmester curves, the loci of possible fixed and moving pivots compatible with all 4 positions, are now being shown. These curves are being shown in red and green, the locus of fixed pivots in one color and the locus of moving pivots in the other color. The curves are calculated and displayed instantaneously, so as the designer moves his design positions around on the screen, the loci showing the possibilities for where pivots could be located track along and change their shape to reflect the instantaneously displayed design positions. This means that certain positions can be used to explore the possibilities for a design. They can be used as control positions. When the designer selects a link based on these Burmester curves, the designer can no longer put the pivots wherever he or she likes, but is instead constrained to position the pivots only on the Burmester curves. Now the designer has selected a pair of links for a mechanism and is exploring the analysis of this particular choice of a linkage. As you see, the mechanism moves the rotor exactly through the 4 design positions, but it has a little unwanted dip as it goes between the design positions. The synthesis only ensures that the mechanism can move exactly through the design positions. To determine the performance between the design positions, one must go through the analysis process. With Kinsyn 7, this happens virtually instantaneously, so one can quickly optimize the performance of the mechanism, not only at the design positions, but also in between the positions. At this point, the designer is starting on a new problem. Rather than use a picture to represent the moving body, the designer is simply using the T-shaped plane icon. The plane icon is shown in both the number 1 and the number 2 positions. The designer just put out a moving pivot and has grabbed a fixed pivot and is sliding it back and forth on the straight line locus of possible fixed pivots for this 2-position problem. As you see, the link is shown both in its reference or number 1 position, and it's also shown dotted in its alternate number 2 position. Grabbing a second moving pivot off the list of icons on the side of the screen completes the coupler triangle for the mechanism. You'll notice that default link shapes have been chosen for display in this case. Since the designer doesn't have actual pictures yet established for his various links, he chose to use the default shapes as shown. Notice that the coupler triangle changes shape and distorts to reflect the instantaneous shape of the mechanism. You can also see clearly here the green and red coupler curve as it changes shape in response to the instantaneous choice for fixed and moving pivots. As the designer moves the pivots around, the shape of the coupler curve, which the instantaneously displayed linkage would be capable of generating, changes. The joints between the red and green branches of the coupler curve show the lockup positions for the mechanism, or the reversal positions. The designer is now positioning a third plane symbol. Notice that 3 circular loci are also shown on the screen. These represent the loci of possible sliders capable of exactly moving the reference body through its 3 given design positions. As the designer changes the design positions, the circular loci change. The designer can grab the slider symbol and move it around to any location on those circular loci. The slider is shown not only in the number 1 reference position, but it's shown dotted in the 2nd and 3rd positions as well. Having picked a tentative slider, the designer is now picking a crank link for the driver for this slider crank mechanism. Now the designer has gone back and is changing the slider position on its locus, and you can see that the coupler triangle instantaneously is updated to show the new possibilities. The white box around the screen and shows that the mechanism satisfies constraints or satisfies requirements that the designer has specified. When the box goes out, it means that the mechanism, even though it can be assembled in each of the design positions, can't move continuously through the positions, or in some other way it doesn't meet all of the performance requirements that the designer specified. The designer can set the signal parameter requirements, and only when all of those requirements are met will that white box flash around the outside of the screen. Now the designer has asked to see a visual animation of the mechanism, the slider crank mechanism that he just designed. Also, the designer turned on the display of the coupler curve, so as the slider crank mechanism moves on the screen, notice that it's tracing out the coupler curve. This is the locus traced by the head of that T-shape. Notice that the T goes exactly through the 3 given design positions. That T-shaped plane symbol really represents a reference coordinate symbol drawn on the moving coupler body. The actual coupler body could be any shape, and that's simply the coordinate system that was used to describe the motion of the body. Now the motion of the moving body is being shown in storage mode. This storage mode is often useful when one is getting a hard copy or for the purpose of studying the envelope of the motion generated. Different parts of the mechanism can be chosen for storage mode or for non-storage mode, or indeed different parts of the mechanism can be completely suppressed from the display to enhance the clarity. Now the designer is putting out a fourth design position, and notice that the Burmester curves squirm around on the screen in response to the changing design positions. Powerful high-speed algorithms within Kinsyn 7 compute the Burmester curves and the coupler curves in real time so that the entire complete coupler curve and the complete set of Burmester curves can dynamically change before your eyes as you position the parts of a mechanism, either the design positions or the pivots on the screen. This makes it very easy for a designer to explore all the possibilities for mechanisms. Changing the slope or the position of one of those design positions slightly has a tremendous influence on the shape of the Burmester curves, and sometimes just the slightest variation in a design position will move one of the Burmester curves over into a convenient location that might otherwise be overlooked using conventional techniques. Notice that as the designer scans one pivot along either the circle point or center point locus, the corresponding pivot moves to its location on the other locus. Now as the designer is choosing the second link for the 4-bar linkage, notice that the complete coupler curve for the mechanism is shown continually is changing as the designer scans along the loci. At each instant, the coupler curve reflects the properties of the mechanism being viewed at that moment. The arcs showing the range of link motion can be turned on and off simply by clicking on the appropriate menu titles on the feedback option menu. Similarly, one can turn on or off the display of the default link shapes, or the display of the coupler curve, or the display of the alternate positions for the mechanism. There's a choice between an instantaneous animation, which takes place during the synthesis process, or a more complete animation, which is done in a separate module of the program. This is the complete animation now being shown. It's possible also to display plots of such things as the input versus transmission angle, or the input versus output angle, or the velocity relationships within the mechanism, and so forth. Of course, this information can also be logged to the printer so that one can see a complete performance display for each mechanism.